Electricity. Introduction. Electricity has an important place in modern society. It is a controllable and convenient form of energy for a variety of uses in homes, schools, hospitals, industries, and so on. What constitutes electricity? How does it flow in an electric circuit? What are the factors that control or regulate to answer such questions? We shall also discuss the heating effect of electric current and its applications. Electric current and circuit. We are familiar with air current and water current. We know the flowing water constitutes water current in rivers. Similarly, if the electric charge flows through a conductor, we say that there is an electric current in the conductor. In a torch, we say that there is an electric current in the conductor. In a torch, we know that the cells provide flow of charges or an electric current through the torch bulb to glow. We have also seen that the torch gives light only when its switch is on. What does a switch do? A switch makes a conducting link between the cell and the bulb. A continuous and closed path of an electric current is called an electric circuit. Now, if the circuit is broken anywhere, the current stops flowing and the bulb does not glow. How do we express electric current? Electric current is expressed by the amount of charge flowing through a particular area in unit time. In other words, it is the rate of flow of electric charges. In circuits using metallic wires, electrons constitute the flow of charges. However, electrons were not known at the time when the phenomenon of electricity was first observed. So electric current was considered to be the flow of positive charges, and the direction of flow of positive charges was taken to be the direction of electric current. It is taken as opposite to the direction of the flow of electrons, which are negative charges. If a net charge Q flows across any cross-section of a conductor in time t, then the current I through the cross-section is I is equal to Q by T. The SI unit of electric charge is Coulomb, or C, which is equivalent to the charge contained in nearly 6 × 10⁻18 electrons. 1 ampere is constituted by the flow of 1 coulomb of charge per second, that is 1 A is equal to 1 C by 1 S. Small quantities of current are expressed in milliampere. 1 mu A is equal to 10⁻⁻6 A. An instrument called ammeter measures electric current in a circuit. It is always the current is to be measured. The schematic diagram of a typical electric circuit comprising a cell, an electric bulb, an ammeter, and a plug key. Note that the electric current flows in the circuit from the positive terminal of the cell to the negative terminal of the cell through the bulb and ammeter. Example: a current of 0.5 A is drawn by a filament of an electric bulb for 10 minutes. Find the amount of electric charge that flows through the circuit. Solution: we are given I is equal to 0.5 A, T is equal to 10 minutes, is equal to 600 S. We have Q is equal to IT, which is equal to 0.5 A into 600 S, which is equal to 300 coulomb. Electric potential and potential difference. Charges do not flow in a copper wire by themselves, just as water in a perfectly horizontal tube does not flow. If one end of the tube is connected to a tank of water kept at a higher level, such that there is a pressure difference between the two ends of the tube, water flows out of the other end of the tube. For flow of charges in a conducting metallic wire, the gravity, of course, has no role to play. The electrons move only if there is a difference of electric pressure called the potential difference along the conductor. The difference of potential may be produced by a battery consisting of one or more electric cells. The chemical action within a cell generates the potential difference across the terminals of the cell even when no current is drawn from it. When the cell is connected to a conducting circuit element, the potential difference sets the charges in motion in the conductor and produces an electric current. In order to maintain the current in a given electric circuit, the cell has to expand its chemical energy stored in it. The potential difference between 2 points in an electric circuit is defined as the work done to move a unit charge from one point to the other. Potential difference V is equal to work done by charge, W divided by Q. V is equal to W divided by Q. SI unit, volt. 1 volt is the potential difference between 2 points in a current-carrying conductor when 1 joule of work is done to move a charge of 1 coulomb from one point to the other. 1 volt is equal to 1 joule divided by 1 coulomb. 1 V is equal to 1 Jc to the power minus 1. The potential difference is measured by means of an instrument called the voltmeter. The voltmeter is always connected in parallel across the points between which the potential difference is to be measured. Circuit diagram: electric circuits and their components. The devices which deliver electricity are called the sources. Lamps, electric engines, etc., which consume electricity are called loads. Switches are used to switch the loads on and off whenever necessary. Hence, the source, the loads, and the switches are connected to form electric circuits. The circuit is called closed when the current flows in the circuit, and when the current does not flow at all, it is called an open circuit. The switch or key helps to make or break the circuit. Components of an electric circuit: cell, source of current, longer line for the positive and shorter line for negative terminal, battery, source of current. A group of cells is called battery. Key or switch, to on and off the current. Closing the key starts the current in the circuit. Rheostat, to vary current in the circuit. A represents variable resistor. B represents rheostat. Resistance or load, to convert the electric energy into another form of energy. Both the ends are fixed, always connected in parallel to the voltmeter or output. Connecting wire or conductor, to connect the various elements. Made of copper with a very low resistance. An inductor or an insulated copper coil. Connected in parallel with a battery of AC source. Ammeter, to measure the magnitude of current. Always connected in series with the positive marked terminal towards the higher potential. Voltmeter, to measure the potential difference. Connected in parallel across the load with positive marked terminal at higher potential. Galvanometer, to detect the current in the circuit. Connected in series in the circuit. Alternating source of current. This source alters the direction or flow of current after a fixed interval of time. Ohm's law. Is there a relationship between the potential difference across a conductor and the current through it? Let us explore with an activity. Set up a circuit consisting of a nichrome wire XY of length, say 0.5 meters, an ammeter, a voltmeter, and 4 cells of 1.5 volt each. First, use only one cell as the source in the circuit. Note the reading in the ammeter I for the current and reading of the voltmeter V for the potential difference across the nichrome wire XY in the circuit. Tabulate them in the table given. Next, connect 2 cells in the circuit and note the respective readings of the ammeter and voltmeter for the values of current through the nichrome wire and potential difference across the nichrome wire. Repeat the above steps using 3 cells and then 4 cells in the circuit separately. Calculate the ratio of V to I for each pair of potential difference V and current I. In this activity, you will find that approximately the same value for V by I is obtained in each case. Thus, the VI graph is a straight line that passes through the origin of the graph. Thus, V by I is a constant ratio. In 1827, a German physicist, Georg Simon Ohm, found out the relationship between the current I flowing in a metallic wire and the potential difference across its terminals. He stated that the electric current flowing through a metallic wire is directly proportional to the potential difference V across its ends provided its temperature remains the same. This is called Ohm's law. In other words, V alpha I, or V by I is equal to constant is equal to R, or V is equal to IR. R is a constant for the given metallic wire at a given temperature and is called its resistance. It is the property of a conductor to resist the flow of charges through it. Its SI unit is ohm, represented by the Greek letter ohm. According to Ohm's law, R is equal to V divided by I. If the potential difference across the two ends of a conductor is 1 volt and the current through it is 1 ampere, then the resistance R of the conductor is 1 ohm. That is, 1 ohm is equal to 1 volt divided by 1 ampere. We get I is equal to V by R. It is obvious that the current through a resistor is inversely proportional to its resistance. If the resistance is doubled, the current gets halved. In many practical cases, it is necessary to increase and regulate current without changing the voltage source. This is called variable resistance. In an electric circuit, a device called rheostat is often used to change the resistance in the circuit. We will now study about electrical resistance of a conductor with the help of the following activity. Activity: take a nichrome wire, a torch bulb, a 10-watt bulb, and an ammeter, a plug key, and some connecting wires. Set up the circuit by connecting 4 dry cells of 1.5 volt each in series with the ammeter, leaving a gap XY in the circuit. Complete the circuit by connecting the nichrome wire in the gap XY. Plug the key. Note down the ammeter reading. Take out the key from the plug. Note: always take out the key from the plug after measuring the current through the circuit. Replace the nichrome wire with a torch bulb in the circuit and find the current through it by measuring the reading of the ammeter. Now repeat the above step with the 10-watt bulb in the gap XY. Do the ammeter readings differ for different components connected in the gap XY? What do the above observations indicate? You may repeat this activity by keeping any material component in the gap. Observe the ammeter readings in each case. Analyze the observations. In this activity, we observe that the current is different for different components. Certain components offer an easy path for the flow of electric current, while the other resists the flow. We know the motion of electrons in an electric circuit constitutes an electric current. The electrons, however, are not completely free to move within a conductor. They are restrained by the attraction of the atoms among which they move. Thus, motion of electrons through a conductor with less resistance is a good conductor. A conductor having some appreciable resistance is called a resistor. A component of identical size that offers a higher resistance is a poor conductor. An insulator of the same size offers even higher resistance. Factors on which the resistance of a conductor depends. Activity: complete an electric circuit consisting of a cell, an ammeter, a nichrome wire of the length L, and a plug key. Now plug the key. Note the current in the ammeter. Replace the nichrome wire by another nichrome wire of same thickness but twice the length, that is 2I. Note the ammeter reading. Now replace the wire by a thicker nichrome wire of the same length I. A thicker wire has a larger cross-sectional area. Again, note down the current through the circuit. Instead of taking a nichrome wire, connect a copper wire in the circuit. Let the wire be of the same length and same area of cross-section as that of the first nichrome wire. Note that value of the current. Notice the difference in the current in all cases. It is observed that the ammeter reading decreases to 1/2 when the length of the wire is doubled. The ammeter reading is increased when a thicker wire of the same material and of the same length is used in the circuit. A change in ammeter reading is observed when a wire of different material of the same length and the same area of cross-section is used. On applying Ohm's law, we observe that the resistance of the conductor depends on its length, on its area of cross-section, and on the nature of its material. Precise measurements have shown that resistance of a uniform metallic conductor is directly proportional to its length and inversely proportional to the area of cross-section A. That is, R is directly proportional to and R alpha 1 by A. Combining equations, we get R alpha I by A, or R is equal to rho I by A, where rho is a constant of proportionality and is called the electrical resistivity of the material of the conductor. The SI unit of resistivity is ohm meters. It is a characteristic property of the material. The metals and alloys have very low resistivity in the range of 10 to the power minus 8 ohm meters to 10 to the power minus 6 ohm meters. They are good conductors of electricity. Insulators like rubber and glass have resistivity that vary with temperature. The below table reveals that the resistivity of an alloy is generally higher than that of its constituent metals. Alloys do not oxidize readily at high temperatures. For this reason, they are commonly used in electrical heating devices like electric iron, toasters, etc. Tungsten is used exclusively for filaments of electric bulbs, whereas copper and aluminium are generally used for electrical transmission lines. Electrical resistivity of some substances at 20 degrees Celsius. Material resistivity. Conductors. Silver 1.60 into 10 to the power minus 8. Copper 1.62 into 10 to the power minus 8. Aluminium 2.63 into 10 to the power minus 8. Tungsten 5.20 into 10 to the power minus 8. Nickel 6.84 into 10 to the power minus 8. Iron 10.0 into 10 to the power minus 8. Chromium 12.9 into 10 to the power minus 8. Mercury 94.0 into 10 to the power minus 8. Manganese 1.84 into 10 to the power minus 6. Alloys. Constantan 49 into 10 to the power minus 6. Manganene 44 into 10 to the power minus 6. Nichrome 100 into 10 to the power minus 6. Insulators. Glass 10 to the power 10 minus 10 to the power 14. Hard rubber, 10 to the power 13 minus 10 to the power 16. Ebonite, 10 to the power 15 minus 10 to the power 17. Diamond, 10 to the power 12 minus 10 to the power 13. Paper, 10 to the power 12. Resistance of a system of resistors. There are two methods of joining the resistors together. Electric circuit in which three resistors having resistances R1, R2 and R3 respectively are joined end to end. Here the resistors are said to be connected in series. A combination of resistors in which three resistors are connected together between X and Y, the resistors are said to be connected in parallel. Resistors in series. Join three resistors of different values in series. Connect them with a battery, an ammeter, and a plug key. You may use the resistors of values like 1 ohm, 2 ohm, 3 ohm, etc. and a battery of 6 volt for performing this activity. Plug the key. Note the ammeter reading. Change the position of ammeter to anywhere in between the resistors. Note the ammeter reading each time. Do you find any change in the value of current through the ammeter? You will observe that the value of the current in the ammeter is the same, independent of its position in the electric circuit. It means that in a series combination of resistors, the current is the same in every part of the circuit or the same current through each resistor. Activity. In the previous activity, insert a voltmeter across the ends X and Y of the series combination of three resistors. Plug the key in the circuit and note the voltmeter reading. It gives the potential difference across the series combination of resistors. Let it be V. Now measure the potential difference across the two terminals of the battery. Compare the two values. Take out the plug key and disconnect the voltmeter. Now insert the voltmeter across the ends X and P of the first resistor. Plug the key and measure the potential difference across the other two resistors separately. Let these values be V2 and V3 respectively. Deduce a relationship between V, V1, V2 and V3. You will observe that the potential difference V is equal to the sum of potential differences V1, V2 and V3. That is, the total potential difference across a combination of resistors in series is equal to the sum of potential difference across the individual resistors. That is, V is equal to V1 plus V2 plus V3. In the electric circuit, let I be the current through the circuit. The current through each resistor is also I. It is possible to replace the three resistors joined in series by an equivalent single resistor of resistance R such that the potential difference V across it and the current I through the circuit remains the same. Applying the Ohm's law to the entire circuit, we have V is equal to IR. On applying Ohm's law to the three resistors separately, we further have V1 is equal to IR1, V2 is equal to IR2, and V3 is equal to IR3. IR is equal to IR1 plus IR2 plus IR3, or Rs is equal to R1 plus R2 plus R3. We can conclude that when several resistors are joined in series, the resistance of the combination Rs equals the sum of their individual resistances R1, R2, R3 and is thus greater than any individual resistance. Resistors in parallel. Now let us consider the arrangement of three resistors joined in parallel with a combination of cells. Activity. Make a parallel combination XY of three resistors having resistances R1, R2 and R3 respectively. Connect it with a battery, a plug key and an ammeter. Also connect a voltmeter in parallel with a combination of resistors. Plug the key and note the ammeter reading. Let the current be I. Also take the voltmeter reading. It gives the potential difference V across the combination. The potential difference across each resistor is also V. This can be checked by connecting the voltmeter across each individual resistor. Take out the plug from the key, remove the ammeter and voltmeter from the circuit. Insert the ammeter in series with the resistor R. Note the ammeter reading I. Insert the ammeter in series with the resistor R1. Note the ammeter reading I1. Similarly, measure the currents through R2 and R3. Let these be I2 and I3 respectively. What is the relationship between I1, I2 and I3? It is observed that the total current I is equal to the sum of the separate currents through each branch of the combination. I is equal to I1 plus I2 plus I3. Let Rp be the equivalent resistance of the parallel combination of resistors. By applying Ohm's law to the parallel combination of resistors, we have I is equal to V divided by Rp. On applying Ohm's law to each resistor, we have I1 is equal to V divided by R1, I2 is equal to V by R2 and I3 is equal to V by R3. From the above equations, we have V by Rp is equal to V by R1 plus V by R2 plus V by R3, or 1 by Rp is equal to 1 by R1 plus 1 by R2 plus 1 by R3. Thus, we may conclude that the reciprocal of the equivalent resistance of a group of resistances joined in parallel is equal to the sum of the reciprocals of the individual resistances. Advantages of parallel connection. A parallel circuit divides the current through the electrical gadgets. Each device takes its required amount of current and operate properly. All devices work with constant voltage. If one component fails, the other components continue to work. Disadvantages of series connection. An electric bulb and an electric heater cannot be connected in series as they need current of widely different values to operate properly. But in series circuit, the current is constant throughout the electric circuit. When one component fails, the circuit is broken and none of the component work. Heating effect of electric current. A battery or a cell is a source of electrical energy. The chemical reaction within the cell generates the potential difference between its two terminals that sets the electrons in motion to flow the current through a resistor or a system of resistors connected to the battery. To maintain the current, the source has to keep expanding its energy. Where does this energy go? A part of the source energy in maintaining the current may be consumed into useful work. The rest of the source energy may be expended in heat to raise the temperature of the gadget. An electric fan becomes warm if used continuously for a longer time. On the other hand, if the electric circuit is purely resistive, only connected to a battery, the source energy continually gets dissipated entirely in the form of heat. This is known as the heating effect of electric circuit. This effect is utilized in devices such as electric heater, electric iron, etc. Consider a current I through a resistor of resistance R. Let the potential difference across it be V. Let T be the time during which a charge Q flows across. The work done in moving the charge Q through a potential difference V is VQ. Therefore, the source must supply energy equal to VQ in time t. Hence, the power input to the circuit by the source is P is equal to VQ divided by T, which is equal to VI. The energy supplied to the circuit by the source in time t is P into T, which is equal to VIT. This energy gets dissipated in the resistor as heat. The amount of heat H produced in time t is H is equal to VIT. Applying Ohm's law, H is equal to I squared RT. That is, V is equal to IR. This is known as Joule's law of heating. The law implies that heat produced in a resistor is directly proportional to the square of current for a given resistance. Directly proportional to the resistance for a given current. Directly proportional to the time for which the current flows through the resistor. Practical applications of heating effect of current. The electric iron, electric toaster, electric kettle, electric oven, and electric heater are some of the familiar devices based on Joule's heating. Electric bulb. In an electric bulb, the filament must retain as much of the heat generated as is possible so that it gets very hot and emits light. It must not melt at such high temperature. A strong metal with high melting point, such as tungsten, is used for making bulb filaments. Electric fuse. Electric fuse protects circuits and appliances by stopping the flow of any unduly high electric current. The fuse is placed in series with the device. It consists of a piece of wire made of a metal or an alloy of appropriate melting point, for example, aluminium, copper, iron, lead, etc. If a current larger than the specified value flows through the circuit, the temperature of the fuse wire increases. This melts the fuse wire and breaks the circuit. The fuse wire is usually encased in a cartridge of porcelain or similar material with metal ends. The fuses used for domestic purposes are rated as 1A, 2A, 3A, 5A, 10A, etc. for an electric iron, which consumes 1 kilowatt electric power when operated at 220 volts. A current of 1000 by 220A, that is 4.54A, will flow in the circuit. In this case, a 5A fuse must be used. Electric power. The rate of doing is power. This is also the rate of consumption of energy. The rate at which electric energy is dissipated or consumed in an electric circuit. This is also termed as electric power. P is equal to VI. P is equal to I square R, which is equal to V square by R. SI unit watt. We have a larger unit called kilowatt. It is equal to 1000 watts. Since electrical energy is the product of power and time, the unit of electric energy is watt-hour. 1 watt-hour is the energy consumed when 1 watt of power is used for 1 hour. The commercial unit of electric energy is kilowatt-hour, commonly known as unit. 1 kilowatt-hour is equal to 1000 watt into 3600 seconds, which is equal to 3.6 into 10 to the power 6 watt second, which is equal to 3.6 into 10 to the power 6 joule.